Today we're going to start talking about a three-dimensional object called a parametrized line, which is a special case of a more general object, which is called a vector-valued function. So by the end of today, we should be able to define this general term, vector-valued function. Because it is a function, we should be able to evaluate it at a given input. Because it is a function, we should be able to represent it graphically. And then we're going to hone in on the specific case of parameterized lines, practice finding its equation, and then we're going to look at the formula for the distance between a point and a line. Now, to define a vector-valued function, I'm going to, first of all, define a real-valued function or a scalar-valued function. And this is the kind of function that you are familiar with from your work all the way since, I guess, algebra. A real-valued function slash scalar-valued function is a function whose outputs is a real number. In other words, the output of the function is a scalar, hence scalar valued. And the typical notation for a function of one input variable where the function is real valued is something like y equals f of x. Now a vector valued function, by contrast, outputs a vector instead of a scalar. A function whose output is a vector. And so the notation that we typically use for a vector valued function is instead of the letter f, it's traditional to use the letter r. We usually use an input variable of t because vector valued functions come up really often in situations where the input is time. As emphasis, we usually represent r with a vector arrow over top, and a vector valued function is going to output a vector where you'll have some formula for the x component, some formula for the y component, and some formula for the z component in terms of the input variable t. This is what it would look like in 3 dimensions. If we were in 2 dimensions, the only difference would be that we would have a formula for the x component, a formula for the y component, and no z component. Now, vector valued functions are used in situations where you have a vector quantity that is not constant, a vector quantity that is potentially changing with time or with position. For example, we know that vectors can be used to point to specific locations. So vectors can be used to represent the position of an object. But if the object is moving over time, then the position vector is changing over time. So the position of a moving object can be represented by a vector valued function where the input is time and the output is a vector pointing to the object's position at that time. Related to this, we can also represent the velocity of a moving object using a vector valued function. We saw that a velocity could be represented as a vector where the direction of the vector was the direction of the object's movement and the length of the vector represent the object's speed. But if the object is accelerating or decelerating, if it's turning in this direction or in that direction, then the velocity vector is not constant and it's changing over time. In such a situation, we can represent the velocity vector by a vector valued function where once again the input is time and the output is the object's velocity at that time. There are also numerous situations where you have a force which is not constant, and the force varies with time. Maybe the force starts out really strong and peters out and gets weaker and weaker as time goes along. Or maybe the direction in which the force is being applied changes. So in that case, we can also represent that with the same vector-valued function where the input variable is time and the output is the force vector at that time. Additionally, a force may vary with position. An example of that would be gravitational force. Gravitational force varies according to one's position relative to the body or planet which is exerting the gravitational force. As you move further away from the planet, the strength of the force decreases, and as you change your position around the planet, the force vector's direction changes. So in this case, we could have an input which is position, and the output would be the force vector at that position. Now let's go ahead and get some practice using the formula for a vector-valued function and evaluating it at a few given input values. So in our case, our vector-valued function says, give me the input t, and this is the vector that I'll produce. The x component will be equal to 2 cosine of t, and the y component will be equal to 2 sine of t. Let's evaluate it at t equals 0, pi half, pi, 3 pi half, and 2 pi. And then once that's done, we have a follow-up question. If the function gave you the position of a moving object at a specified time t, along what kind of path would the object be moving? Okay, so first I will evaluate the vector-valued function at the input t equals 0, which means that I need to replace t with 0 in the formulas for the two components. So cosine of 0 is equal to 1, so 2 times 1 is 2. Sine of 0 is 0, and that gives me 2, 1. So off to the side, I'm just going to make a note of the terminal point of this vector. When t was equal to 0, this vector pointed to the point 2, 0. Now, moving on to pi over 2, if we plug that t value into our vector-valued function, this time the cosine becomes 0 and the sine is positive 1. So let me go ahead and let me note that when t is equal to pi over 2, this time the vector-valued function is pointing to the point 0, 2. So then we go to r of pi. Moving to the left side of the unit circle, we have cosine of pi, sine of pi, each multiplied by 2, so we get negative 2, 0, and that is pointed to the point negative 2, 0 on the xy plane at t equals pi. And of course, 3 pi over 2 will just point straight down, giving us 0, negative 2. At the final value of t equals 2 pi, then we're back on the right side of the unit circle, so we're back to the point 2, 0. We've evaluated the vector-valued function at these 5 input values, and the question is, if this function gave you the position of a moving object what kind of path would the object be moving along? We started on the right side of the unit circle, and then we curved up toward the point at the North Pole. Then we curved down to the point at the left side of the unit circle, then to the bottom, and then back up. And as t continued to increase, this vector valued function would continue to spin around and around and around the unit circle like the hand of a clock. So in answer to this question, this object, whose position is represented by r of t, would be moving in a circle of radius 2 counterclockwise. This kind of drawing that I have given on the right hand side here of this problem is how we represent a vector valued function graphically. If you want to graph a vector valued function, the first thing that you want to do is graph all the terminal points of the output vectors. For example here, I didn't graph the entire vector to 0, I only sketched in that vector's terminal point, the point 2, 0. I sketched in the point 0, 2, the point negative 2, 0, and so on and so forth. And based on the general pattern and behavior that I observed, by plugging those 5 points into this function, I could infer that the vector valued function would always point to a location on this circle of radius 2. So I sketched in all the points on this circle of radius 2. That's the first step to graphing a vector valued function. But I also included arrows so that someone looking at this graph would know whether the circle was being traversed clockwise or counterclockwise. So when you're graphing a vector valued function, the next thing that you have to do is add arrows to indicate the direction in which the path is traversed as t increases. Let's get some practice graphing the following 3 vector valued functions. Now the first one that we have is exactly the same as the one that we had in the previous example. We had r1 of t, which was a circle of radius 2, traversed counterclockwise. So I've sketched that path with a couple of details just to make it clear how that path was obtained. The most important thing that I have drawn here is that the path traced out by the vector valued function is a circle, and I've added arrows to that circle to indicate to the viewer that as t increases, then we're traversing the circle in the counterclockwise direction. Now let's try it with the second vector valued function, where we have r2 equals 2 cosine minus t, 2 sine minus t. Now in this case, let's plug in a couple of different input values for t to see if we can get a read on the object's movement. So for example, if I plug in t equals 0, then I'll have cosine of 0 sine of 0. So this will give me the same vector 2, 0, which is pointing to the same terminal point at the right side of the circle. However, if we move to a slightly greater value of t, such as pi half, then I have cosine of negative pi half, negative t. I have sine of negative pi half, negative t. So that points straight down on the unit circle, which would give us 0 minus 2. 0 minus 2 at t equals pi half. Now you can continue inputting different input values to this function and plotting the associated terminal point, but it already seems to me, based on the nature of the formulas that we've been given for the x component and the y component, that this function will also trace out a circle, except this time we are traversing the circle in the clockwise direction. So almost the same, it creates the same path, but different arrows to indicate that it's being traversed in different directions over time. Now for R3 of t, if I plug in t equals 0, then I'm still pointing to the point to 0, so the same starting location. But if I plug in t equals pi over 2, because that t gets doubled, I'm now looking at 2 cos pi, 2 sine pi, which is already all the way on the left side of the circle. If I wanted to reach the top side of the circle, then I would have to plug in a much smaller t value, pi over 4, so that when that t value is doubled, I get cosine of pi over 2, 2 sine pi over 2, which does point to the top of the circle. 0, 2 is achieved at t equals pi over 4. So this circle is also being traversed counterclockwise, but it's being traversed counterclockwise twice as fast compared to the original vector-valued function r1. Now I have gone ahead and I've indicated the times at which these points were achieved, but that's not a requirement when you are graphing a vector-valued function. I've done it as an optional step for additional clarity. But in general, as a rule, the graph of a vector-valued function only has to communicate the path in which the object traveled and the direction along which the path was traveled. The graph of a vector-valued function does not have to communicate how quickly the path was traveled. That was an optional step taken by me. Let's do another example. Let's graph the vector-valued function where we have a linear equation in the first component, 3 times t minus 1, and a linear equation for the second component as well. Let's graph a few points on this vector-valued function, and let's see what shape is formed. So maybe first I'll plug in t equals 0. If t is equal to 0, then I get 3 times 0 minus 1, and I get 2 times 0 plus 1. So on the xy plane in 2 dimensions, since I have a 2-dimensional vector-valued function, I'm going to indicate the terminal point where x is negative 1 and y is equal to positive 1. Then when t increases slightly, and I get 1, then plugging in t equals 1, I get 3 times 1 minus 1, which is equal to 2. And I get 2 times 1 plus 1, which is equal to 3. So that puts me up here, roughly speaking. And what if I went backwards in time and considered minus 1? If I plug in minus 1, then I'll get negative 3 minus 1, which is negative 4. negative 2 plus 1, which is negative 1. And so that would be located, 2, 3, 4, minus, that would be located here. Now this drawing is not perfect by any means, but notice that these points are already beginning to line up. And if I plotted more values of t, if I was even more careful, we would see it lining up even to a greater extent. So I'm going to connect the dots with my best attempt at a straight line. This is the graph of the path traced by the output values of the vector valued function. And I'm going to add directional arrows to indicate that as t got larger, the path that we traverse moved toward the upper right. So if our vector valued function has a linear equation for both the x component and the y component, the shape formed by the graph is a line. And so we call such a vector valued function a parametrized line. So here's a general theorem. Suppose we have some vector called d, non-zero, and we also have a vector which we'll call r0, which is pointing towards some point x0, y0 that's been given to you. If you want to find a line which passes through the point x0, y0, and which points in the direction of the vector d, then that line is the same thing as the graph of the vector valued function, where you take the vector d, scale it by the input t, and add the vector pointing toward the given initial point. The vector d here is called the direction vector, and it's acting a little bit like the slope of a line. The vector r0 points toward the initial point, so it's acting a little bit like the intercept of the line. Let's compare that with the example that we just had. When we graphed this line, we saw that it passed through the 2 points where we had negative 1, 1, and we had 2, 3. Let me call this guy the point P and this guy the point Q. Now if I looked at the vector stretching from P toward Q, that vector would have the coordinates final minus initial, 2 minus negative 2, 3 minus 1. Additionally, our line passes through the point negative 1, 1. So the vector valued function that passes through the point negative 1, 1 and points in the same direction as the vector 3 minus 2 did indeed have the equation where we take the 3, 2, scale it by the input t, and add this initial given point, 3 times t minus 1 in the x component, 2 times t plus 1 in the y component. Now in this context, the letter t is called the parameter. This function is given the special name a parameterized line. Now, the autocorrect feature on Microsoft Word always gives me some trouble when I type parameterized without this E in between the T and the R. But I think that technically speaking, this mathematical term is properly spelled without that second E. Whatever you decide to do is fine. Parameterized or parametrized. I think one is more American and one is more British UK type English. So called parameterized line because it's given by the output of a function a function having an input variable known as the parameter. So let's get some exercise and let's practice finding a parameterization for the line which passes through the point 3, 1, 2 and which points in the direction of the vector -2, 1, 0. So this question is asking us to find a vector valued function r of t whose graph traces out the line described in this paragraph. Now the direction of the line is given by the vector -2, 1, 0, which implies that the direction vector is -2, 1, 0. We also know that the line must pass through the given point 3, 1, 2. So the vector which points to that location, angle brackets 3, 1, 2, is the quote-unquote initial point that we need for our formula. So we can take the direction vector -2, 1, 0, multiply it by the parameter t, scale it by t, and then add the initial point 3, 1, 2. I can leave it in this format, or I can use component-wise scaling and addition to combine it, giving me r of t equals -2t plus 3, 1 times t plus 1, 0 times t plus 2. Now, from time to time, you may not be given the direction vector for your line, and you may need to calculate it yourself. So, in this exercise, find a parameterization for the line passing through the 2 points 2, 5, 8 and 1, 1, 3. Now, if a line passes through those 2 points, which I'm just sketching in very rough terms over here on the right side, then a vector which points in the same direction as the line can be found by calculating the vector stretching from the first given point to the second given point. So I can find the direction vector for this line by, for example, finding the vector stretching from P to Q. So I can do terminal minus initial, I can do terminal minus initial, terminal minus initial, and I can get the direction vector -1, -4, -5. For the initial point contained in this graph, for the initial point r0, you can use either P or Q. All you need is some point contained by the line. So I might just use P because it's first in the alphabet. It was the first one listed. So a parameterization for this line could be given by the direction vector scaled by the parameter t plus a vector pointing to the point P. Now I want to note that this is one possible answer amongst a collection of many possible correct answers. There were many opportunities while we were answering this question to make other choices. For example, we could also choose to have the direction vector not be the vector from P to Q. It could just as well be the vector from Q to P. We could have our R0 point to the point P, but it would just as well work to have our R0 point to the point Q. So depending on the direction of your direction vector, depending on your choice for R0, we already have 4 different possible variations of the final answer. However, every single one of them has a graph which is equal to the given line. It's just that different answers are going to traverse the line in different directions, and they may start at different positions on the line. Now the formula for a parameterized line between 2 given points can be found using the technique above, where we took the difference between the coordinates of the 2 points to get a direction vector, and then we went ahead and plugged that direction vector and one of those initial points into the formula for a parameterized line. However, if you want to, this is totally optional. If you want to, there is an alternative formula for the parameterization of a line that runs between 2 points. And this is sometimes called the LERP formula. LERP stands for linear interpolation. So if you want to find a parameterization for a line passing between 2 points, let's take a vector R0, which points to one of the points that's given to you, let's call it P, and you have a vector R1, which points to the second point that you're given. And then a parameterization for the line between them can be found by taking 1 minus t, that number, and use it to scale the vector R0, and take the parameter t and use it to scale the vector R1. This formula is equivalent to the process that we used in the previous exercise. For example, if we let R1 point to the point Q in the previous example, Q which was equal to 113, and if we let R0 point to the point P in the previous example, 258, then using this LERP formula for the parameterization of a line between these 2 points, we would have R of t equals 1 minus t times R0, which is 258, plus the scalar t scaling 113. And you can actually check that if you do the vector arithmetic to combine these 2 vectors, then the result will be exactly the same as what we got before. Now, one of the cool examples of how this is actually used is to raise between 2 different colors. In the land of computers, a color is represented by a triple of values. One representing the red value, one representing green, and one representing blue. So a color is basically the same thing as a point in 3-dimensional space. And passing from one point to another is like changing from one color to another. Let's find a parameterization for not the line, but for the line segment whose endpoints are 255 red, 153 green, 0 blue, which is equivalent to a lovely shade of orange, and the point 0 red, 204 green, 255 blue, which is a nice shade of light blue. Now for this, I can use the LERP formula to find the full line between these 2 points, the infinite line, which says that we can do 1 minus t, the scalar 1 minus t, times the vector pointing toward the first location, 255, 153, 0, and then the scalar t, scaling the vector 0, 204, 255. Now at the moment, this is currently an infinite line. And I only want a finite line segment whose endpoints are at the two given points. So the solution to this problem is that I'm going to make the line become finite by restricting the domain, by restricting the values of t that I am allowing myself to plug in to this parameterization. Let's plug in two different t values to see how I might want to restrict the domain. When t is equal to 0, then 1 minus t is equal to 1. And when t is equal to 0, the scalar in the back is just 0. When t is equal to 0, the vector points to the initial location or color that was given. The vector points to 255, red, 153, green, 0, blue. But if I plug in the number 1, if I plug 1 into this formula, then the first scalar, 1 minus t, becomes 1 minus 1, which is 0. So I get none of the orange portion, and I'm getting entirely the blue portion. So if you're using the LERP formula and you want only a line segment instead of a full infinite line, all you have to do is restrict the allowed values of the input to the interval where t goes from 0 to 1. If you don't artificially restrict the domain, then it's implied that t can go all the way from negative infinity to positive infinity, which will give you a line that's infinite in both directions. But if you restrict the allowed values of t to the interval 0 to 1, then it will only give you the line segment t equals 0 points to the first point, t equals 1 points to the second point. So I just wanted to record some quick footage to show you how this actually would work in a program in a short animation to transition from one color to another. So for simplicity's sake, I'm just over here in the Unity game engine, and I've opened up the script in the C# language. And to start with, I'm just going to define a three-dimensional vector, which is pointing toward the color orange in terms of RGB values. And similarly, I have a vector in 3 dimensions, a vector 3, pointing toward the blue color in RGB values. And then I'm going to set up a third vector, which is going to represent some smooth transition between orange and blue. We're going to start at t equals 0, an initial time, the left-hand side of the endpoint of t values for our line segment. And we're going to continue until t reaches a value of 1. And roughly speaking, each frame, we're going to generate a vector, which is found by lerping between orange vector and blue vector. So here we see that formula, 1 minus t times vector number 1, plus t times vector number 2, and then just some gibberish to make it display visually on the screen. So here we go, back into the Unity project. Here we can see our orange color on the screen, and if I hit play, it will run that lerp formula, and we can see the color transition over time. Now I wanted to discuss with you one particular application of some of the ideas that we have been talking about. Not because this particular application is any more or less important than any other application, but it just gives us a good opportunity to exercise our knowledge of the concepts that we have covered up to this point with regards to vectors and lines. So let's try and find a formula for the distance between some arbitrary point P in either 2 or 3-dimensional space and some line in either 2 or 3-dimensional space that has a direction vector d and which passes through a point Q. So let me sketch this situation. We've got some point P in space, and we've got some line also in space, which we know contains the point Q. And we also know that this line corresponds to a direction vector d. When someone asks for the distance between a point and a line, they're asking for the distance as measured in the most efficient way. If we went from the point to the line in the most efficient way, going straight from the point to the line so that our journey to the line made a right angle to the line itself, the distance in this problem is the length of this blue line segment. Now look at what happens in this drawing. If I fill in the vector from the point P to the point Q, then I have created a right triangle. And if I indicate this angle, let's say theta, then from right triangle trig, we know that the sine of the angle theta is equal to opposite divided by hypotenuse. In this case, the opposite is the distance that we're going to want to calculate, and the hypotenuse is the length of this vector stretching from the point P to the point Q. So in other words, the distance that we're trying to calculate is equal to the vector PQ length times sine of the angle theta. Now looking back at this image, the angle theta is interesting because the angle theta is the angle between the vector PQ and the vector D. So we can use that formula from the cross product section of the course, which said that sine of theta times the length of the vector PQ, the length of the first vector, and the length of the second vector was the same thing as the length of the cross product of those two vectors. Now our expression contains the length of PQ, but it doesn't contain the length of D. So in other words, length of PQ times sine theta is equal to the magnitude of the cross product divided by the length of the direction vector for the line, and this quantity was equal to the distance. So from this, we get a formula for the distance. We can calculate this by taking the length of the cross product and dividing it by the length of the direction vector. Let's try this in action. So I went out to Math Stack Exchange, found a question about a parametrically defined line and the distance from that line to a point. So here's the problem on Math Stack Exchange. The student is trying to find the distance between a point 1, 1, 1 and the line passing through the point 0, negative 1, 1, and with a direction vector of 1, minus 2, 2. So here is the only and thus the accepted answer. Seems a little bit involved, but it is a very intuitive answer. So in this case, the student has the point P equals 1, 1, 1 in space, and the student's line passes through the point 0, minus 1, 1, and the vector has the direction 1, negative 2, 2. And so the vector passing from P to Q is equal to terminal minus initial, terminal minus initial, terminal minus initial. So let's go ahead and let's take the cross product, ijk in the first row, then the entries of pq in the second row, and the entries of d in the third row. Negative 2, 0, negative 2, 2, scaling I, minus negative 1, 0, 1, 2, scaling j, plus negative 1, negative 2, 1, negative 2, scaling k. So calculating those entries, we have minus 2 times 2, which is negative 4, take away 0. This determinant is equal to negative 1 times 2 minus 0. With an extra negative becomes positive 2. And then for the k component, we have negative 1 times negative 2, so that's positive 2, minus 1 times negative 2, all in total 2 plus 2, which is 4. So to finish this out, let's go ahead and let's find the length of the cross product, which is just the square root of the squares of the entries. 16 plus 16 is 32, plus 4 is 36. Wow.
Wow.
Exactly 6. And the length of the direction vector d plus 2 squared, so 1 plus 4 is equal to the square root of 9. So wow, that's actually also a whole number. Incredible. You can tell that this really was a test question because the answer has worked out to be something incredibly nice. Usually my test questions are not this kind. The distance is equal to the 6 divided by 3, which is simply 2 units. So that concludes what we're going to talk about in the realm of parameterized lines. We talked about, first of all, what is a vector-valued function and how is it drawn? What does the equation for a parameterized line look like? How do you find the equation given a point on the line and a direction vector? And how do you find the equation given 2 points on the line? We talked about how to restrict the full line to a line segment by restricting the domain. And then we used some general properties of the cross product, as well as some right triangle trig to find a formula for the distance between a point and a parameterized line.